STEPCon 21 is in full effect. We are ready to start the show. Let's make some noise for our two stars of the show. We have Professor Matters and Dr. Boom. Welcome, virtual audience. Welcome, view audience. Dr. Boom and Professor Matters, give it up for them. Make some noise.
All right. Thank you. Thank you. And welcome. I'm Professor Matters.
And I'm Dr. Boom.
And we together work on a nuclear fusion research project down in San Diego, where we bring light elements together at 150 million degrees.
150 million degrees?
10 times higher than the center of the sun, the temperature. Yeah, it's awesome. And we have to use motion, understand motion in our science that we do. So today we brought some little demos to talk with you about motion, okay? Oh, what have you got here, Dr. Boone?
Well, I have a little demo here. We're going to be talking about Newton's motion. And Newton has three laws that we're going to talk about.
Okay.
It's object at rest tends to stay at rest. Object in motion tends to stay in motion. It's the same law.
Okay.
It's kind of like called the law of inertia. So, put that word in there. It's up there. And force equals ma.
Okay.
Which is mass times acceleration.
Okay.
Is the force.
And the third one?
Third one is action reaction.
Action and reaction, like a rocket when the rocket takes off and the gas is blown out the back.
Right.
Very cool. So what is this? It looks like a big keychain.
It is. And so what I'm going to do here is I'm going to rotate this, I'm going to put it in motion, and then we'll see what happens.
Oh, look at the pattern. Oh, look at that.
It's cool, right?
I like that. That is cool. And that's from a simple chain that's rotating. Very cool.
Okay, so let's see what happens if we change the mass of the chain. Do things change?
Oh, it still has a nice pattern to it.
Wow, you see that? So only one side goes kind of wiggly and the other side goes straight.
Yeah.
Kind of interesting. Why does it do that?
Whoa.
Oh.
Wow, that's very cool. I like that. I like that a lot. It's simple. Oh, what you got there?
This is my Mr. T chain.
Mr. T chain.
So the same thing. One side is squiggly and the other side straight. Oh, did you see that? It kind of came up and went over.
It did, and it
all the way down.
It did. It kept its height there for a while. Oh, look at that.
This is my white one. It's plastic, and same thing. The straight side's on one side.
Oh, that's beautiful.
And let's see what happens when I drop this.
Oh, so the same thing, very similar. These are all chains of different sizes, different masses, different weights, and yet they behave in a similar manner. Very awesome. Very cool. You know, I was at the, I was putting some chain in my glass the other day, and you know what happened?
What?
Some of it fell out.
Yeah.
And it looked like
Did it keep going?
Kind of kept going, yeah.
Kind of kept going like these.
Yeah. It was very cool. Very cool.
Well, we have a demo here where it's a chain being pulled out of a glass, and we need two assistants here. Let me introduce Dr. Genevieve on my left.
And Mr. Lee over here now.
Mr. Lee.
Genevieve here is a graduate student at University of California, Irvine. Relatively close to here, so.
And Mr. Lee is a soon-to-be pilot. We'll see how far he flies. And so what we're going to do here is we're going to have a race, okay? And so the race is going to be see who can empty their bucket. Now these are 100 feet of chains each bucket, each vase, and I'm going to start them and watch what happens to the tops of it at the vase. Watch how it goes over the top. And so we're going to get a countdown here. Ready? 3, 2, 1. Watch, see how it goes up over top? Look at it. Let's see, who's going to be first? Who's going to be first all the way out? Oh! The good doctor made it.
Very nice. Now that chain kept going up over the top. That's kind of what I observed, but I did not have a 33-meter chain like you did here.
No.
That's very awesome.
Exactly.
And you know what I would have done to get the chain out? Dumped it out.
Okay, let's give him a hand.
All right, very good. Thank you. All right, so getting over there.
I'm getting this here tube, and this tube is going to be a chemical.
Okay, so we saw some mechanical things. Mechanical things are physical things that you can see and touch. How about if we do something similar with some gas? And Dr. Boom here is going to explain what's moving in this tube. We need the lights down, please. Thank you.
Okay, so we have, this is a demo on combustible fluid. And so we'll have a, you'll see.
So what are you doing there, Dr. Boone?
Well, I'm releasing some gas in here and I'm igniting it. And you see the pressure wave going down the tube. And so we have action-reaction because it's burning as a flame front and it's pushing itself out. And then it's also burning towards the gas. Oh, did you see that? Came out the other side.
That is very cool. Oh, very nice. And I can see some of the products of the combustion in there. I see water vapor condensing in there.
Water vapor. And so I have to ignite it with a spark. And the spark is a plasma.
We'll talk about that shortly. Very cool. Very cool. All right. So, go ahead. Now, I was in the lab the other day, and I dropped a balloon onto a little nail. What do you think happened? It popped, right. However, once I took a few nails together and put the same balloon on there, it didn't pop. And I think the reason why...
I have one nail.
That's a nail, all right.
Should we actually see if it pops or not?
Should we? Now that point, you're putting all that pressure, all that force on that little point, and it made a lot of pressure to pop that. Now, what I noticed is when I had many little nails, it didn't pop. So I made a little nail piece here. Well, just watch, it's just this little set of nails, and I can do this all day long. With many nails, the force I'm pushing down is spread out over those nails, and so the pressure on this is quite low. Now, if we just had something other than a balloon to put on here.
We should put a person on here.
A person?
A person.
Do we have a volunteer? Oh no, we can use Dr. Genevieve there.
The good doctor will do it.
All right. Would you like to see her on a bed of nails? Okay.
All right, so hop up here, Dr. Genevieve.
Now, you may have seen this
I'll give you
on
a hand.
some show or whatnot, but this is real. These are real, nails.
Nails, all right.
Now,
are you okay?
Not only is
Perfect.
this a bed of nails, this is a sandwich of nails.
Now we're going to put on a safety shield.
So Mr. Lee here is going to help us
Is that good?
make the sandwich of nails.
All right,
you want to
so
see that?
We're going to put on a blanket of nails on her stomach. Now, force equals MA. Okay, so the force of the nails at the points is equal to the mass times the acceleration, and it hurts at about 16 pounds per nail, but I don't think she's even close. So now we have a tray here. What do you think I'm going to put in the tray? I'm going to put a cinder block in there. And so guess what I'm going to do to the cinder block? I'm going to break it.
Now, what we're going to see here, ideally, if we were to push down slowly here, we'd have a mess on our hands. But what we're going to do is hit this quickly, and the inertia of that block, the inertia means resistance to change in motion or change in movement. It's going to tend to stay there, and we'll see what happens.
We will see what, Dr. Genevieve will see what
Well,
happens
I'm
also.
going to back away. I'll go get some bandages here.
Okay, you want to give me a countdown?
3, 2, 1. Ooh.
Ooh.
Okay, now in all science experiments, we have to look at the results, right? And the results are going to be to see if we observe any leaking.
Let's see.
Any
no
leaking?
leaking. No.
No leaking. All right.
You
Very nicely
survived.
done.
Wow.
Nicely done. So we'll go ahead and remove this. Nicely done. So the idea here is that we were able to spread out all the force that she was on there over a large area, and it made for low pressure. And so it was good. I don't know how comfortable it was, but it was quite nice. Now, our buddy over here, 500-year-old Isaac Newton, came up with a lot of things from Galileo. Galileo and Newton made up lots of concepts on motion, although they lived at different times. One of the things that we call today is this little Newton's cradle, where we have these little balls, these little spheres, and we can hit one in and one goes out.
Wow.
Very
one
cool.
in and one out?
Yeah. Watch this, though.
Oh.
We can get two in.
Two in and two out.
And two
Whoa.
out. Okay. Very, very cool.
I have something with more pizzazz than that.
So
I have something that you'll...
these are... Oh, my goodness. These are bowling balls.
Yes, indeed.
Ah,
So I got them from a bowling alley that was going out of business because most bowling alleys are going out of business because of COVID. And so here we go. Let's see.
okay, one in.
Yeah?
What do you expect to go out? One. All right. One in, one out.
One in, one out.
Can you do two?
Okay, here we go. We're going to do two.
Two in and two out.
How do we get two in, two out?
Well, when you're lifting those up, you're giving them some potential energy. And that potential energy turns into kinetic energy or energy of motion.
Yeah.
And the momentum of the balls, all of this is conserved. So the amount of energy you're putting in on that side
Right.
ends up on
Comes
this
out that
side.
side. Oh.
Okay.
So it's like the conservation of momentum.
Yes, and conservation just means to kind of keep it all in the same
So if
system.
we put three in.
Three in, three out.
Oh.
Very
Three in,
cool. How
three
about
out.
four? Can you do four?
Can we
you
do
reach?
four? I can reach over and we can do four.
Oh, look at that. Four in and four out.
Yeah.
Very cool.
How about five?
Ooh.
Should we do five?
Five in.
All right. Here we go. Five in.
Oh,
Oh.
and five out.
Yeah, well, that's what you'd expect, right?
That is what we'd expect, right? We didn't add any more energy than we put into it. And so when we move five balls, we move five balls.
We do.
Very nice. Nicely done, Dr. Boom.
Thank you.
Now, Dr. Boom mentioned something about plasma a moment ago. I'd like to show you some more examples because where we work, as I mentioned before, with a 150 million degree plasma. Now, the plasma here is not 150 million degrees, but nevertheless, let's see. I have this high voltage unit here, and it will put out 30,000 volts on this side. All you have to think of is that voltage is energy. So it's a lot of energy. And I have a metal key here. And if I could have the lights off, please. Let's see what happens. Isn't that cool? What does this look like? Looks like lightning. Now, it looks like lightning. It can look like a spark plug or the spark in a spark plug in your car. It can look like the sun has plasma in it as well. And what that means, the plasma part here, is that the outer part electron, remember we have an atom with the electrons going around it, that outer electron or more is ripped away from the atom. Very cool. Now I have some little glass tubes here I'm going to give to Genevieve. And inside the glass tubes are some atoms of gas. Right now we can't see them. They're clear, they're colorless. But I can go ahead and excite them by getting this electric field close, and I can ionize them into a plasma. Okay. Very cool. This one happens to be neon. That characteristic color is actually made up of not only orange, but green and blue and red and lots of other ones. Let's see what I have here. I have neon here. let's see. Oh, here's an argon. Here's some argon. Now, argon is readily in the environment. Very cool. Now, nice thing about plasma, when you rip that electron away, now it can behave like an electrical wire and actually move electrons through there. So I'm going to go ahead and see if we can. Okay, so we're exciting it, and now we're going to ionize it. Here it goes all the way through. Now, the way you might see this at home is in a fluorescent tube. Here's one that's half coated. So the bottom part here is the argon we see, and this upper part here on the inside has a coating, a paint on the inside that tends to put out white light when excited by the atoms on the inside of there. Very cool. So all your fluorescent lights have plasma in them. And you can put a different coating in there for different colors as well. All right, very cool. So that's our little introduction to plasma. Inside of there, the molecules are moving back and forth, left and right, up and down. And when we excite them, they change their character a little bit. And if we actually ionize them, then they turn into something that can carry electrical current. Very, very cool.
We are at California Baptist University, CBU in Riverside, home of the Lancers. And there he is, the Lancer. Lance it up, y'all. And we're here to look at the real-world applications of those ideas you've been hearing about. The motion, the physics, the inertia, forces, all those things. And we're gonna have a lot of fun looking at these. Our students talk to you about those things. So are you ready to discover more? Come on in with me.
Hello, my name is Adonai Pearson. I am a transfer student from a community college to California Baptist University, pursuing mechanical engineering in my junior year. On this object, we can observe the airflow on the component. This airflow is a high velocity airflow that goes on the object on the top and below. We use this force to observe on the object to see the weakness and the strength. And this force is nothing but a Newton force. It has a velocity and has an acceleration of force on the component. And it will have those devices for engineers to see the weakness and the strength of the object for the best design there is.
Yeah, we definitely wanted you guys to see that this stuff that you're seeing right here. Oh, how are you guys doing? All right. Oh, you guys were mesmerized by the cheesiness of the guy in the video. But definitely, guys, all this stuff that you're seeing, you use it in the real world. Use it for actual things. And the wind tunnel like that, they test objects, and it's pretty much like a big toy, you know, something like one of the things that you guys might play with now. Do you guys spend a lot of time playing with what, Minecraft? Do you guys do Minecraft? Do you guys still do Legos? Do you guys still do Legos? Do you guys still like Pokemon here? I mean, okay, so look, all those things that right now you guys are playing with, that's kind of what scientists and engineers do. They play with things. They spend all day trying to destroy something in the wind tunnel, right? So it's amazing. That's what you could do if you become a scientist or engineer. Play around with stuff. But let's have some questions. Were you listening? All right, let's see. All right, so the bed of nails. Remember the bed of nails? You know, yes. And just a warning, guys. I know some of you are thinking you're gonna go to Home Depot and buy 50 nails. Don't try this at home, all right? So, yes. Don't put like put your cat on it, put your dog on it. You know, poor doggy on the bed of nails. Anyway, so someone could lay on the bed of nails because A, the nails are evenly distributed over a large area realistic in the lower force producing area. B, the nails are white. Oh, that's kind of racist. And C, the nails are softer at the tip. So, okay. So who thinks the answer is A? Raise your hand. A. All right. What about B? Anyone think it's B? And let people guess. It's okay. This is a judgment-free zone. Not a criticism free zone, adjustment free zone. And C. Who thinks it's C? All right, the answer is A. Give yourself a round of applause. Okay, we got one more question to test your knowledge. And teachers, this is going to be on their participation grade today. No, it's not. You're not getting graded. Anyway, plasma. We talked about plasma. Plasma is a wonderful state of matter, right? It really matters. It does. So A, plasma is an ionized gas that can be a lightning bolt, a spark plug, the sun, it's even capitalized, sun, or all of the above. All right. So what can plasma be? Who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? All right, let's see what the answer is. It is, those things. You guys were paying attention. Do you guys remember that lightning storm a few days ago? Did you guys see that lightning storm a few days ago? So y'all were seeing plasma, just plasma. It wasn't Pikachu. It wasn't Pikachu like my son said. All right, it was plasma or any of those electric electric Pokemon. Is that what they are? Electrical, whatever. All right, yeah, electric Pokemon. Well, awesome. More stuff to learn. More demos coming up. Are you guys ready for more? Let's get some more going.
Professor Matters, you asked me to put this
Professor
rod,
Matters, yes.
I mean, Dr. Boom.
Put that into that.
Put this down
into the wood.
Well, I went over to the museum over there and borrowed a 15th century vase.
Yeah.
And I put this on top.
Yeah.
And I banged it down.
And you broke it. The vase.
The vase, yeah.
15th century. It's really old.
15th century, very, very old. And I don't think they'll notice it though because I taped it up.
Yeah, well,
I taped it up. I think it'll work okay.
Taping, but the glue would have been better.
But how can
But you don't need to do that. You can use Newton's law of inertia. The wooden block has inertia, and it will tend to stay in its place. And so if I hit it with an impulse, with a hammer, I will push this rod right through the wood.
No. It is going up. Let me try that.
See that? You're going right into the wood.
Wow. I mean, this is really on there. I like that. So you mean I didn't have to use that 15th century vase after all?
That's right. You can save your money.
Oh. Well, the museum will be happy to know that. Okay. All right. That is cool. Now, here we are at the Cafe of Commotion. And in the Cafe of Commotion, things move, things fly, things roll. And we have on the menu today something called hoops and nuts, and then something called plates and cloths. So what have you got here?
Well, this is hoops and nuts, and can I have some of my helpers up here?
Mr. Lee and Genevieve?
Yes. And so we're going to do this one at a time, so we'll see without any interference. So what I'm going to do here is I'm going to use the inertia of the nut here, and it's holding up the hoop is holding up. I'm going to knock out the hoop, and the inertia of the nut will just keep it in space, and then it'll drop down into the bottle. You think so? This is like contactless delivery. All right, here we go. 1, 2, 3.
That didn't work.
I missed. Okay, so let's try Mr. Lee here.
So we want to use the inertia of that nut. Inertia means resistance to motion.
It's a bigger hoop, yes indeed, so it will fall farther. And let's see if he'll be quick enough to move it. Oh!
Resistance to change.
All right,
motion,
well, we have,
I should say. Change it.
we have one more chance
Okay,
here.
Ooh, this is the hardest one of all. This is the hardest one of all.
Oh. Nobody can do it.
Let me try it. Let me try it.
Okay.
Just quickly. Thank you.
Quickly. Yeah, nice catch. Catch it in the bottle. Whoa!
There we go.
All right.
Thank you. Okay, so inertia is very important. It's the resistance to the change in motion. Whether something's already in motion or something's at rest, if you try to change that motion and it's difficult, that's a property called inertia.
Now, we have a set of plates here, and the inertia of the plates and the tablecloth and the friction should enable us to... What?
These are the hotel plates.
They won't mind.
They won't mind?
No.
Okay.
The hotel's on our side.
Oh, are they?
Yeah.
Okay.
If we pay them.
Oh.
So what we're going to do here is we're going to have Mr. Lee pull the tablecloth out from underneath these plastic. These are plastic, just so they don't break. And we're going to see how he does. Are you ready?
All right.
Let's give him a countdown. 3, 2, 1. Oh, my goodness. I thought you practiced this. Thank you.
Oh, nicely done. All right.
Was this the practice run?
So, luckily those were not breakable.
Yeah. So now we're going to give the good doctor here a run for our money. And so we have my mom's expensive china. And look at this. I have 6 matched cups. These are special matched cups with the blue rim, the thick one on the bottom and the little one on the bottom. And we're going to stick that on there just to give it a little more challenge, okay? And so let's see. How are we going to do? 3, 2, 1. Yo!
Oh, nicely done.
That was really amazing.
Nicely done. Very nice.
Good job.
Very good. Very good. Now, we've been seeing things that kind of sometimes rotate, sometimes are in a straight line. And let's see what we can do with...
Here, let's just put this on the cable here.
Oh, that's my bicycle wheel.
Yeah.
What are you doing with that?
Well, we're going to borrow it.
Where's the other cable to hold up this side?
We don't have one.
Well, we need another cable to hold up this side.
Well, if we use Newton's laws, we probably don't.
Well, okay. How do we do that?
Well, if we spin the wheel, we have the momentum of the wheel.
Momentum.
That will cause a torque around the middle, so it'll cause it to be stable.
Okay.
Let me show you. I'll spin it up.
Oh, we didn't need that. Yeah, give it a... We didn't need that second one after all. You want to do it a little faster?
Yeah. You got to hold that.
Let's do this a little bit faster here. There we go. Nice. Angular momentum, angular inertia, rotational inertia.
Yep.
Very nice. So we didn't need that second cable after all.
Right, angular momentum. The Earth has angular momentum around its axis.
Yes, it does.
And the moon has angular momentum around the Earth.
Yep.
And the Earth has angular momentum around the sun.
Yes, anything that spins has got angular momentum.
And unless something from the outside affects it, comes in from the outside and affecting it, it just keeps going.
It will.
Yeah. The only thing stopping things here is friction.
Very cool. Let me take this off.
Okay.
Yeah, but
can you feel something?
Yeah, when I try to turn this, it feels like it's wants to, I don't know, kind of a force or something on it.
You got the force? Can you feel the force?
I can feel the force.
Well,
so, may the force be with you. They said it. Okay, so let's try this. Genevieve, come up here. Okay, go ahead and have a seat. Now, this is the Lazy Susan, not her, but the thing down here, and it rotates.
No. I challenge you to move around the axis of the table. Okay, you're paddling. Looks like you're paddling the air. like a canoe. No, I would go the other way. The other way is not very helpful. So let's see if we can change that. Now let's see if you can move by twisting.
Oh, that's what I was feeling, but I wasn't on a rotational axis there.
That's right.
Oh, she's gonna go all the way around.
So this is like an ice skater when they go around and pull in the mass going around the arms.
Their arms in or something.
Yeah.
And every time she turns that, it's producing a torque around there. Go faster, faster, faster. Very cool. So satellites use this up in space, and rockets use it, and ships use it. And I even saw one time a locomotive used it, a big train back in the 1800s. They tried this out with a big wheel like this that they got spinning, and then that locomotive could just be on one set of wheels. It needed only one rail to go down.
Wow.
They thought they'd save money by not having to put down both rails. Very nicely done, Jean-Pierre. Very nicely done. All right, so we have linear, we have rotational motion, and that was rotational motion kind of horizontal with the Earth, or parallel with the Earth here. What's this?
So I have a bucket of water here.
A bucket of water.
Indeed, and it's on a like a four string
Here, why don't you
platform
come
here.
over here a little bit?
And what I'm going to do with this is I'm going to spin it around in a circle.
I'm going to stand back. I saw what happened earlier.
Yeah, but so you're ready for this? Okay, let's see if we can spin this water around and around.
Oh, that's awesome. All that water staying in there.
Stayed right in there, right? So we're not supposed to get any water on the stage, but you
No.
know.
Ah! So these were ping pong balls. They mimic water molecules. So let's actually have them do it with real water.
Now you see. You think it'll work? What's going to happen if it doesn't work? You want to do it to you? Like this? You ready? Are you ready to get wet? All right, here we go. You're getting wet. So if I stopped it at the top, what would happen? It would fall, but I can't stop it because I can't stop it from going around. So there you go.
All right. So now had we cut that string at the top, it would not continue on its rotation here. It would just head off somewhere over there to Newton right there. Very cool. Now, that's right, you remind me. At home, I had the water on in the faucet. When I turned the water off really quickly, I heard a bang in the wall where the tubes are, where the pipes are. And this, I just can't quite do this right, Dr. Boom.
Yeah?
This is called a water hammer.
There you go. It's from the shoulder.
Okay, there you go. That's what I heard. I heard that little banging sound. And as I was looking carefully, it looked like that little slug of water actually went up
A little bit.
and then pulled down quickly.
A little bit.
Oh, but when it went up, there was nothing down here.
Vacuum.
Vacuum, the
Vacuum.
absence of most things there.
No gas.
And so then that vacuum and the pressure in here pulled that down really quickly.
It did.
And it made that bang.
So the inertia of the water and the tube goes down, and then there's a vacuum created, and then the water comes down and hits the tube.
Yes, and the energy of that water coming down comes out as sound.
Right.
Very cool.
And so I have a bottle here. This is a clear bottle. It's a liter bottle. No, it's maybe more than a liter. It's a 1 quart, 1.8 fluid ounces. So I'm going to knock the air out of this water, and then what I'm going to do is hit it with a heavier hit, and then you'll see what happens. The stress point is right around the edge here. Let's see if the bottom breaks
So you're
out.
going to try to do the same thing. That slug of water is going to effectively be up in there and then pull down quickly.
Yes, and it's going to hit.
So we should hear a nice sound.
Right.
Let's listen for that sound.
Wow, just the bottom.
That was a lot of energy to pop
Yeah.
that out.
So with about 200 pounds of force hitting that.
And it wasn't because you were just pushing down and pushing air
No,
into here.
no.
Wow, that slug of water went up and then down compared to that bottle.
Indeed.
Very interesting. The water hammer is...
Water hammer is when the water is moving at a velocity in your pipes in the home, and it changes velocity very fast. And so it turns, what usually happens when you turn the spigot on and off, or when your sprinklers go. So we have another demo here.
Now
Lights
you
up,
all
please.
saw these earlier, and you feel the air coming out, but you don't know what
Lights
is
up, please.
actually making...
Lights up, please. Lights up,
You're
please.
not quite sure what the geometry is. And these things actually go pretty far. These little air bazookas. And so they're very stable. They come out as rings. It's kind of a surprise that they come out as rings out of here. And,
Yeah.
And you can look online too and see porpoises do this. They'll make a little vortex down below under the water, and then they'll play with that little
So good.
vortex there.
Yep.
So-
Go get that one.
Oftentimes bigger is better. And so these, okay, keep in your seats. Keep in your seats. These are little rings that can go out. All right. Very cool. Oh no, no, out there, out there. Very cool, very cool. So these are Airzukas. That's a nice class project right there. Thank you.
So this is the CBU SAE racer, one of the racers. It's like a real race car. Oh my goodness. I guess, let me see if how we... Oh my goodness, I can imagine how this thing moves. It has an engine and it turns wheels. But I wonder how you get something like this to stop. Have you wondered that? How cars stop? Well, maybe someone in the lab will tell us. Let's go there.
Hi everyone, my name is Kevin Zelaya. I'm a senior here at California Baptist University, and I'm studying mechanical engineering. I'm blessed to be a part of the Formula SAE team here at California Baptist University, and I am on the driver controls team, which is in charge of the brakes, as you see here. So the way the brakes work is as your car is moving forward, and so this is your wheel, there's two forces that are being applied, which then causes the car to stop. Those forces are then converted into thermal energy, or as you may know, temperature and heat. So these brakes get really hot, but because the car is stopping, that thermal energy goes into the air. So in order to measure that and see how hot that our brakes get, we have sensors along here to help measure that and better predict how hot our brakes are gonna get. So that's a little bit about what I do. Thank you, and I hope you love science.
Okay, so yes, again, so you guys could see how some of this science is used in the real world. CBU actually brought one of their racers So I don't know if you got a chance to go out there and actually see their little race car and even touch it and get in it. It's hard to get in it. I mean, let me tell you, it's really hard to get in that thing. It's crazy. But they actually get timed for getting in it. In fact, if they don't get in a certain amount of time, they lose points. It's kind of crazy. Are you guys ready for more questions? Have you guys been listening? Have you? All right. Goodness gracious. A lot of learning going on today. Let's see our next question. The bottom broke out of the glass water bottle when hit by the rubber hammer. You saw that the whole bottom completely came off. That's crazy. And why did that happen? Was it A, because there was a vacuum created between the water and the bottom, which forced the water to return to every day and broke the bottle out? Is it B, the bottle has too much water in it? Is it? Oh, I guess it's D. All right. Hey, give yourselves a round of applause. All right. All right. Okay. We'll get to the next question. The fog ring stayed in the shape of a circle. You know those rings that were being shot at you, just all violently? Why did it stay in the shape of a circle? Was it A, because fog only comes in circles? The circle of fog. Because a vortex was created by the Izuka and is stable. Or was it C? It's lighter than air. Who thinks it's A? Who thinks it's A? Okay. Who thinks it's B? Who thinks it's C? Who thinks it's D? Who thinks it's E? What's after E? That was that took you guys a little long though. All right, let's see. The answer is it's B. All right, give yourselves a round of applause. Good job. And virtual audience, good job, because I know you were playing along with us. Give yourselves a pat on the back if you're online, like this, or like that, or like this. I don't know what you're gonna do. But thank you for watching online, and thank you for enjoying this these segments. Virtual audience, live audience, are you ready for our final set of demonstrations? I said, are you ready for that final set of demonstrations? All right, here we go. Let's finish off the show.
All right. Thank you, Carlos. Now, we've talked about linear motion, circular motion. How about just a partial circular motion? You've seen things like this before, a pendulum. It may be a grandfather clock or grandmother clock. It's simply a mass on a stretchless cord. Just simple. So what can we do with this, Dr. Boone?
We can swing it back and forth.
We can.
And we will have some effects that we can notice about this. Can I have two assistants up here?
Oh,
Mr. Lee, Dr. Genevieve. Now, what we want to do here, we have carefully positioned these two volunteers in precise places. So if Genevieve holds this up to her nose and releases it, it should not hit Mr. Lee in the nose or the chin. Okay, and so what we're going to do about this is we're going to notice how long it takes to go from one to the other and come back. That's a full cycle. Okay, so we'll just count down 1, 1,000, 2, 1,000 when we release. Okay, ready? 3, 2, 1. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5. Oh, it's about 5 seconds, maybe 4. Stop. Good reaction. Okay, let's do that again. Release. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. Too fast, yeah. So it's about 4.
Yes.
Okay, so let's see if it changes if we increase the mass. Is it the mass that affects how fast it goes, or is it something else?
So there's only 2 things we can change on this. The mass, how much is on there or how little is on there, and the length. And we'll see how the period is that time.
Let's see. 3, 2, 1. Go, release. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000.
Oh.
Wow, it's about the same.
It is the same.
Wow, so what's... Keep going. What's slowing it down is the friction in the system. So the friction and the air friction is going to slow it down until it finally will stop. Okay, now stop. All right.
So this is fantastic because it shows 2 types of energy. One is potential energy, where it's up high.
Wave pin.
And then the other is kinetic energy when it's swinging down through its low point. So that potential energy is being changed to kinetic energy, and then it goes back to potential energy and back to kinetic energy. Now, we changed the mass on this, and we found that the period was the same. Now, let's change the length on the pendulum and see what happens. This is definitely something you can make in the classroom. So Dr. Boom has set up these little yellow bowling balls on some thread here, and we're going to pull them back and release them all at the same time. You want me to turn that around or leave that there?
I think it'll work here.
Okay. The longest threads are in the front here, and the shortest ones are back here.
Here we go. 3, 2, 1.
Oh, that's cool.
Now, if you go online, you can look these things up, and it's called the wave pendulum, and they make them even out of bowling balls.
These are nice. So the period, that is the time for the forth and back motion, is different for each of those.
It is.
Now, you know what's really interesting here is they started out all as one line, and watch, they'll go back as one line eventually. Very cool, a very great school project for you to do. Go back to the snake motion.
All right, there it comes back now.
That's how we kind of started. Now they'll just for a moment, they're back in phase.
Synchronized, yep.
And then they'll go back out of phase and start all over again.
Right, and it's all about the adjustment of the length of the string.
Yes.
Okay.
Square root of the length. Very good, Dr. Boom. Thank you, thank you.
Hi everybody, my name is Ashley Nicholas. I'm going to be a senior studying chemical engineering at California Baptist University this fall. The reason that I love science is because I love knowing how things work and how everything fits together, and that helps me solve problems in the real world. So one of the things that I had to do last year in my junior design class was design a chemical-powered car. So we decided to go with a car that has a pressure system. So we have this tube right here, and we put chemicals in it that generate gas, and the gas build up and build pressure, and when it releases, it pushes this piston that powers the gears, and that turns the wheels. So our big focus was inertia, which is getting the car in motion, and it'll stay in motion until gravity slows it down. So we get to do tons of exciting and fun things like this. I'm super excited to work with people and work on cool projects and get to represent girls in STEM.
Hi guys, my name is Hunter Wantz. I'm a third-year mechanical engineer at California Baptist University. Some of the reasons why I chose mechanical engineering as my major is from a young kid, I've always loved to problem solve and learn how and why things work together. And combining that with my natural liking for math and science, I felt that this field was the most applicable for me. So behind me we have a balloon and a guy holding a needle. Let's see what happens. Wow, would you look at that? The balloon exploded. So the force is acting on it, the balloon's gone, so the force of gravity causes it to fall down, and there's nothing holding it on the sides, so it causes it to flare out at the same time. Science is amazing and fun, and I hope to see you guys in the STEM field soon.
I hope that we see you in the STEM fields someday, right? Yeah, did I scare you? Yes, we're almost done. It's all right, man. We're almost done, dude. We're almost done. All right, we have a couple more questions just to make sure that you guys were listening. Were you listening? Were you really? Yeah. Come on. Y'all are too young to be tired. Come on. What do you mean you're not tired? Y'all are too young to be tired. All right. Are you ready? A few more questions. Let's see if you were listening. Let's see this next question here. Question number, I think it's 5, I think. All right, let's see here. Question number 5. When 2 bowling balls were put in the pendulum, the period or frequency of the time it takes from end to end, did it stay the same? Did it increase? Or was it shortened? Let's see. How many of you guys think it's A? Raise your hand if you think it's A. Raise your hand if you think it's B. Raise your hand if you think it's C. Let's see what it is. The answer is, it's A. Give yourselves a round of applause for listening. I'm a little weary of this thing in front of me, but what do you think it is? Goodness. All right, good Lord. Okay, let's go to the last final question, all right? All right, here we go. The wave pendulum. You guys remember the wave one? The one that was like, woo, 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 right? That one? Moved at different periods due to A, the high atmospheric air pressure pushed it out due to 10-second line equals A. It was orange. It could only move one way. Interesting answers. Oh, wow. What did I kick? I kicked one of these things. Hey, soccer with a ping pong. Okay, what do you think it is? A, B, or C? Let's see what it is. It is A. All right. Good job, everyone. We're ready. We're ready for the grand finale. Are you guys ready? Did you guys learn a lot today? If I gave you a test, would you pass it? What do you mean no? All right. Let's go to our finale. Let's bring up the good doctor and the good professor. Let's go. Let's go.
All right. So we have power here, Dr. Boone.
I got it. I found the power. Ready?
Well. So.
We have our team up here.
Yes, so thank you for coming out today. I guess we have our grand finale here, and we'll go ahead and use some of the things we learned. We have the chemical car from Cal Baptist, and we had Dr. Boom with his little chemistry part going around the beginning. And inside of here, we have a little bit of combustible fluid. We have a little plasma that we'll make inside of there, and we'll see if we can shoot a piston out of here. Ooh. Are you ready? Give us a countdown.
3, 2, 1, go!
Oh, wonderful. Thank you. Thank you very much for coming out. Make sure that you get covered. Make sure you get covered in science, all right? It's a very cool thing. So cover yourself in science, cover yourself in knowledge, and have fun with it. Thank you.
All right, a round of applause for our wonderful crew. All right, take a bow. Take a bow, something. All right, let's hear it for our wonderful science show crew. Come on, let's give it up. Energy. And I want to thank all of you for coming here. Our virtual audience, thank you for watching us. You can wave at them. Want to wave at them, real crowd? Thank you for watching and learning about science with us, all right? Oh, boy. So everyone have a seat, and we're going to be dismissed in an orderly fashion. So go ahead and have a seat, everyone. And Our stewards will dismiss you. Thank you for coming. Thank you for coming out, having fun with us, learning about science, all right? Have a wonderful rest of your day. Have a safe trip home. Have a wonderful lunch, whatever it is you do. Yes, indeed. Thank you for coming out. Yes, you can watch this again on our virtual platform. You can actually go back and watch this again, and also go to the virtual conference and see all kinds of things when you get home. All right. That, if you watch the first show, if you go back and watch the first show, you'll see what it's all about. That's called a teaser.